Thank you all. It's good to have this webinar with you. I'm really honored that you would take time to listen to an idea that we have worked on here. I'm joined this morning by Dan Allen. He's a psychometrician at Western Governors University. He's working on his PhD. He'll have some observations to share with us later in the webinar. And Barbara Foster is a psychometrician at the American Board of Obstetrics and Gynecology. We have slides from her. She will not be joining us. We're excusing her because she's in meetings in Washington, D.C. I have my colleague, Marcus Stott, who I will turn the time over to at a certain point in the webinar to talk about some of the slides, who has helped me a lot on these slides and a lot of the things that we're talking about today. So, again, thank you for coming. Let's go ahead and start. Next slide, please.
Hey Dennis. I was remiss. I forgot to take care of housekeeping. Attendees, please note that everyone is on mute. However, it's because we have so many attendees, we need to keep everyone on mute. However, on your GoToWebinar dashboard, there is a utility where you can ask questions. And so please feel free to lob questions to Dennis and team. We'll stop periodically and address some of them. Otherwise, we'll have Q&A at the end of the session. The session will last less than an hour, and it is being recorded. So both the slides and the recording will be available to all registrants and attendees. Thank you. Dennis, sorry, back to you.
Okay, let's go forward. Okay, so here's what we're going to do. We're going to talk a little bit about classical item analysis, just one or two slides. Then we'll talk about the idea of what's behind the key strength analysis. We'll do a little bit of derivation. For those of you who we'll have a few formulas. We'll try to keep that part brief. But I know there's some in the audience who will want to see those formulas. There are probably some who want to see more than these formulas. And definitely we're willing to engage with you on that. After we go through that, then we'll have Dan Allen present, then we'll present Barbara Foster slides, and we'll have some conclusions and wrap up. So let's go forward. So classical item analysis is a technique that is used a lot. I know you all know this, but just to review, it is used for screening items that aren't performing properly, performing poorly. Typically, there are two main statistics that are used. That's the p-value, which was the proportion of people who answer the item correctly, and the point-biserial correlation, which measures how well the item aligns to the test score, the test construct. The typical rules used with these statistics are very low p-values indicate very hard questions. If the question is so hard that it's below the guessing level, often that question will be discarded and set aside. It's not suitable for the target audience. On the other hand, very high p-values indicate very easy questions. In those cases, again, those could be set aside easily because they're not measuring very well. And what we call low point-biserial correlations or low discriminations. Often those will be set aside. So these are very easy to understand statistics. They're easy to implement. They're used widely. Probably the most widely used statistics for classical item analysis. Other statistics are used, but we're not going to talk about those today. But these are very good at flagging poor items, or poorly performing items. Next slide, please. So the idea of key strength analysis is instead of using a single measure on an item, let's pool the data across all of the items and all the responses. Let's build a model, and then let's compare answer choices for the same item to see which ones are relatively the strongest. And by doing that comparison of the correct answer and the most appealing distractor, we can perhaps come up with some reasons why the items are not performing well. This analysis relies upon high-performing test takers, those who are knowledgeable, because, and it's often the case, they will report problems with the answer keys, problems with the test, with the items, and they will usually choose the correct answer. So if they're all wrong, then it's likely that this analysis won't work very well. Now, also we look at frequencies, and it's usually the case that very easy questions, the correct answer is the most frequently chosen answer. But it's not necessarily the most frequently chosen for hard questions. So let's go forward. So the classical item analysis is built, so we built this on a classical item analysis on that framework. It's already been tried out and tested. And we're going to use point-by-serial correlations. They discriminate between the high performers, the low performers, and the things we're going to look for here are problems with the items that are typical. That is, an item that might be miskeyed. The answer key might be just a little bit weak. It's not really obvious that it's a really good answer. Or there might be multiple correct answers. You know, it might be ambiguously keyed. Another distractor might be a reasonable alternative correct answer. And the way we're going to do this is we're going to calculate some probabilities and make these use these probabilities to make inferences about the items. Next slide. So we're going to modify the point-by-serial correlation coefficient. And the first thing we're going to do is we will exclude the item score from the test score. This is usually called the corrected point-by-serial correlation coefficient. It's also known by other names. But what it does for us is it places all the answer choices, the correct answer and the distractors, on the same playing field so we can compare them. There's not any kind of implicit bias built in that favors the correct answer. And it allows us then to look at what if, you know, kind of simulation. Well, what if this was correct or that was correct? Okay, so we'll calculate these corrected point-by-serial correlations for the correct answer and for all the distractors, and then we will scale it appropriately. We're going to call this statistic the Z-star statistic. We will use Z-star to calculate our probability that a choice is an answer key. Let's go forward. So we start off with this formula, which is the formula for the point-by-serial correlation. The X's are the item scores, the Y are the test scores. Remember, we've excluded the item from the test score. So, you know, that changes for every item. And now, so we're going to move forward. I don't want to talk about this form of the formula. Next slide, please. Okay, so after some algebra, and this, you can see this in a lot of different texts, we have this form of the point-by-serial correlation. We have this 1 over the square root of n minus 1 factor outside, and then we have this inside quantity inside the braces, which is the average of the people who answer the item correctly, subtract the overall average test score, and then we divide by the quantity in the denominator on the left would be our typical standard deviation or standard error for the mean for y bar 1, and we multiply that quantity by the square root of 1 minus pi. So that's an equivalent representation of the point-by-serial. The reason this is good is it allows us to talk about generalizing it to look at all the distractors and use the same formula. And I have all the definitions of these terms down below. So the important thing to realize here is on the far right we have Z sub I star. This is for the ith item, divided by the square root of n minus 1. So this quantity, Z sub I star, is the quantity we're interested in. So let's go forward to the next slide. Now, this Z sub I star depends on all of the right things statistically, all the right quantities. And the way my motivation for saying that is if I go to sampling theory. Under sampling theory, suppose we take a random sample of n units or observations from a population of size big N, and then we say, what's the distribution of the sample mean, y bar? Well, expected value is the population mean, and the standard deviation is that quantity sigma sub y divided by square root of n times 1 minus f, where f is the proportion of items or units sampled from the population. So F, in this case, corresponds to P, the proportion of people answer the question with that distractor. And so it's proportion of P, proportion to answer the question with that distractor. And also, and it's also known in sampling theory as the finite population correction factor. So if we take that all together, standardized value is y bar minus y double bar divided by that standard deviation value, which happens for our case to be the point-biserial correlation times square root of n minus 1. In other words, this is Z star. Okay, let's go forward. We've seen enough of these formulas. Looks like we have a poll.
Yeah, so we've got our first poll question. Are you going to launch that, Rochelle, or am I? I can. All right. So the question is, which statistics do you typically use for detecting poorly performing items? Select all that apply. And then you'll see the options there. And we'll give people a few seconds to respond. Looks like about 10 more seconds. We've got a majority of folks that are responding. 10 more seconds, and we will close the poll. And share the results. So, Dennis, can you see
So,
the results?
this is interesting. Everyone is more or less using the classical item analysis. It's tried and true. It is the method of choice. Upper lower 27%, about 1/4 of the people are using that also. Person fit statistics, then fit or outfit. Those are IRT-based statistics. So that's less frequently used. Not surprised in any of these, but it's very good to see that a wide variety of methods are being used by the audience. Thank you.
All right, I'm going to hide the slide, Dennis, and we can continue with the presentation.
Okay, I'm going to turn time now to Marcus Scott, my associate, and let him talk about these slides.
Okay, so at this point we're going to show some graphics related to what we've been talking about so far. So this was some sample data we used. There were 154 examinees taking an exam with 100 items. And we calculated the Z-star for all the people who were answering incorrectly. That's this red curve here. And Z-star values for the people that were answering that chose the correct answer. That's this blue curve right here. So as you can see, the right answers had higher Z-star values. That makes sense because people answering this question correctly or probably know the material better and would hence do better on the exam, have a better average score than the average score of all the people taking the test. Just take a look at some of the numbers here. So for the low Z-star values, -6, this is down here in the negatives, it's that's where we see the distractors showing up. Between -1 and 2, there's a bit of some overlap. So just because the Z-star is close to 0, it's not going to be, if you go either way, whether that corresponds to a correct answer key or an incorrect key response. And then finally, in the higher values of Z star, like I talked about, you start to see more of the correct responses. And you may be thinking, hey, you could have fit a normal curve over these. We will be doing that later, and we'll show you that result as well. Next slide, please.
Marcus, really quick.
Yes.
We've got a question on that slide. If we go back, please. What is the y-axis representing?
Oh, so the y-axis represents a frequency. So this is actually just, we bend these like we were making a histogram, and just instead of using columns, I chose to connect it with a line. So, so for instance, over -4, so let's see. So on the red curve at -4, there's a dot at about 0.05. So that would mean 5% of the incorrect answers on this exam had Z star values that were between like the -5, -3 that were in that bin. So these represent just the frequencies of how often they were showing up. And
great. Thank you.
You're welcome. Next slide, please. Okay, so now we want to calculate the probability that the choice is a key given the Z star value. However, that's not as straightforward. We can easily calculate the probability of Z star given that our answer choice is indeed the key. That's using those probability values that's using the information we have on the graph on the previous slide. And thankfully, Baezs Rule allows us to invert this probability so that using the one that's easy to calculate, we can just get the appropriate scale factor using the probability that the choice is a key over the probability of Z star to get the probability that we're actually looking for. And so the denominator of Baezs Rule is going to be expanded using the law of total probability. So that's this next equation here. So this is the math behind it. I won't go any further than that. So now we'll just start seeing it in action. Next slide, please. Okay. So as I said, we can overlay some normal curves of the distribution of Z stars corresponding to incorrect responses and Z stars corresponding to correct responses. By the central limit theorem, the Z star should be normal as the number, and as Dennis mentioned earlier, the method is a lot more powerful as the number of items goes up. And one requirement that we'll have, for the probability function should be a monotonic increasing, and if you do a whole bunch of calculus, you're guaranteed that will happen if these two normal distributions have equal variances. So looking at the pictures, you can tell that these were designed to have normal variances. We satisfy that condition by pooling the variances together. And so now we have these normal distributions overlaid. We can use probabilities from these normal distributions. We can use the probabilities of answering correctly or incorrectly. And we have all the pieces we need for the Baezs rule that we showed on the previous slide. So next slide, please. So now, using the formula for Baezs rule we showed earlier and the information we got on some of the previous slides, you can calculate the probability that the choice is a key given a specific value of Z star. Now, earlier, we saw that in the lower values of Z star, the blue curve, which corresponded to the correct answers, was flat out 0. And you see that here for Z star values -4, -3, up to -2. There's pretty much a 0% chance of that response being an answer key. Between -1 and 2, if you were to look back on a previous slide, there was some overlap between the two distributions. So it could go one way or the other. And you see that here. Between -1 and 2, it's not guaranteed that it's a key, but the probability is indeed increasing. However, once you get from about a Z star value of 3 on, it's almost guaranteed that answer choice is indeed a key. And we saw that on the previous two frequency graphs where the high Z star had just values from the blue curve, and the red curve was 0 at that point. So next slide, please. So now what we want to do is we want to use this kind of curve to analyze the correct answer and also the distractors. A previous slide mentioned that you calculate the key strength for the correct answer and the distractors. And so now we want a way of classifying the numbers that come out of this. So we decided to keep it pretty simple, and we set a threshold at 50%. If a probability was less than 50%, we said that was a low key strength. If a probability was greater than 50% or equal to, we called that a high key strength. And now we have a table set up where, depending on, you want to take a, oh, sorry, actually, let me backtrack just a moment. So you want to take a look at the key strength of the answer and compare it to the highest key strength that you saw in the distractors. And so the first column says whether the answer has a low key strength or a high key strength, and the first row says whether the distractor has a low key strength or a high key strength. So now the 4 entries in the table in the bottom right corner are the different classifications it could have. If the answer has a low key strength, so it's less than 50%, and the distractors have low key strengths, also less than 50%, we say that this is weakly keyed. And what that means is really no answer choice is really standing out. And we'll see a graphical representation of this later on. Going over to the right, if the answer has a low key strength, but the distractor has a high key strength, that's a potential miskey. So that means the knowledgeable students were choosing one of the distractors instead of what is considered the correct answer. And so that might be a sign of a miskey there. Out of these 4, the bottom left, so if the answer has a high key strength and the distractor has a low key strength, well, that's what we want to have happen. We want the correct answer to really stand apart from all the other distractors. So if that happens, that's a normal, good item. And finally, there's the case where the answer has a high key strength and a distractor has a high key strength. Well, that means that there are 2 possible correct answers to this instead of just the one that's marked as correct. And in that case, we say the item is ambiguously keyed. And so the next 4 slides will show examples of these 4 classifications, and you can see it in action. Before we go on, the 50% doesn't have a scientific basis. We chose that because it's simple and easy to do. If you choose to implement a key strength analysis in your program, that threshold can be moved around as you see fit. So next slide, please.
So Marcus, one of the
Yes?
questions, and I think you're getting there right now, one of the questions is how do I apply this to an individual item? And I think that's where we're going on these next slides. Is that right?
Yes. Okay, so the key strength analysis is something that you perform for an individual item. When I was writing the formula for Z star, I left an I subscript on it, meaning you calculate a Z star for one specific item, and you calculate for each distractor, for each answer choice to that item. So a specific item will have X many Z star calculations where each Z star is just depending on one of the answer choices that you have. So I hope that answers the question. I can elaborate more on it if needs be. But our first example is a good key. So this is using one of the items from the 100 items used to make those plots earlier. There's a table at the bottom. It shows the response, just A, B, C, or D, its Z star value, and the corresponding probability. So response A had a Z star value of 3.25, and the probability that it was a key was 0.99. The next highest distractor was answer choice B. It had a Z star value of 0.25 and a probability of 0.06 of being a key. On On all these graphs we'll be showing you, the correct answer is going to be colored gold to separate it from the others and make the plot easier to see. And we drew in the 0.5 line since we use that as our threshold for considering a strong or a weak key strength. And then answer choices C and D, very low Z-star values, practically a 0 probability of being an answer choice. So this is what you hope most of your items will look like. And you may notice that these probabilities aren't adding to 1. That's not a problem. So all this is saying is answer choice A has a 99% probability of being an answer key. That does not mean that there's a 1% chance that the answer key is either B, C, or D. All that we're talking about is A. It may be that the item has no correct answer, and if that was true, then just because one had a certain probability of being a correct answer does not guarantee that the correct answer lies in some of the others. So these probabilities will not necessarily add up to 1. Sometimes they do, but it's not an issue. Next slide, please. All right, example 2. This is a potential miss key. So this slide looks very similar to the previous one. All I did is I changed the correct answer from A to B. You can see that B is now colored gold. So answer choice A had a Z-star value of 3.25 and a probability 0.99 that it is the correct answer. B, which we are considering to be the correct answer in this case, has a Z-star value of 0.25 and a probability of only 0.06. So since answer choice A, a distractor, had a high key strength, and the answer choice B, the correct answer, had a low key strength, this would be labeled a potential miss key according to that table we showed earlier. And once again, C and D have no chance of being the correct answer. Next slide, please. All right, here's an example of a weak key. And this is another easy situation to see where the probabilities don't necessarily have to add up to 1. So the correct answer A has a weak key strength. The key strength is only 0.32, the Z-star value of 1.0. B, once again, low key strength. C and D are low. None of these is clearly standing out, so we call this a weak key. When a key is weak, there's confusion among the examinees and nothing really seems to stand out, and you see that going on here. Next slide, please. And the last example, an ambiguous key. So here we have 2 answer choices with very high key strengths. Answer choice A has 0.99, and answer choice B, which is the correct answer in this case, has a key strength of 0.9. So once again, there's confusion. You have knowledgeable students choosing both of these answers, but really neither one seems to stand out. They're both high up there, and it's possible that both of these are correct answers, or they're highly related to each other in a way that would cause knowledgeable students to select one which should be selected the other. So this is an example of what it would look like.
Hey, Marcus, we've got a question.
Sure.
And that question is, when using Eitman, the distractor analysis point-biserial should be negative. How does the Z-star compare to Eitman analysis of distractors?
So, Marcus, I'll go ahead and answer that question.
Okay.
So, if you went back to the formulas, Z-star, when Z-star is equal to 0, that corresponds to a correlation coefficient value of 0. So when Z-star is negative, the distractor analysis part of those point-biserials will be negative. So in general, when you have negative point-biserials, you'll have a negative Z-star. That answers the question. Just remember, we're using the corrected point-biserial correlation where the item has been removed from the total test score.
All right, thank you very much.
Okay, well,
I'm sorry, Marcus, I couldn't understand that. Next slide.
I will next turn back.
So,
Marcus, sorry, Dennis, we had a tough time hearing Marcus there.
So anyway, Marcus said he's turning the time back to me because those are the slides I asked you to talk about.
Oh, gotcha. Okay.
Okay. So we did this small validation study, and it's kind of a strange study, I admit, but I call this answer key estimation or answer key imputation. So we're going to assume the key is not known. Now let's look at the data where we moved from the system the knowledge of what is the correct answer key. And we want to check how well this algorithm will do in actually extracting the answer key out of the data set. So we start with a guess, and the guess is the most frequently selected choice. We use that as our tentative answer key. And then we will calculate all these probabilities, and then based on the questions where the probabilities indicate a different key is the correct one, we use that key, and then we'll reiterate it. Usually this procedure takes about 3 or 4 iterations, sometimes only 2, and then you settled in on what appears to be the correct answer key. So I did this for 12 different exams, and then I looked at the accuracy, how many we were correct when we were supposed to be correct, etc. And our accuracy varied from 81% extraction to 99% extraction. This little algorithm obviously isn't going to be able to select when we have 2 different answers as being correct keys. Or if there's no answer that is a correct key, it's not going to be able to know that. Next slide. Okay, so here's my summary of my little validation study, my 12 exams. You see I had varying numbers of examinees, different numbers of forms, different numbers of items on the forms, different numbers of items in the pool. Some of them had field test questions or non-score questions. And just looking at the accuracies, you see that 99%, 90, 85%, 91, etc., 96, 96, 96. We definitely saw some association with correctly or with the errors and like deleted items or field test items. So that's important to realize. Field test items usually do not perform as well. They're tryout items. That's reasonable to understand why you would have more errors with field test items. And just a little bit of that background. I'm not going to belabor this and go on to it in a lot of detail. So let's go forward, next slide. So you say, well, why, just one thing, just as an aside, why would you do this? Well, it's about once a year I get working with some data where it looks like the exam has been stolen. The thieves have worked out the answer key, and I want to know what answer key is they're using. So I can use this in order to find out the answer key. I can find out the errors they've committed, and that can help in terms of security analysis. Let's go forward.
All right, we're going to launch, let me make sure I'm not on mute. We're going to launch the next poll question, and that is, what is the most common error found in an item that was discarded after field testing? So we've got a number of options here. We'd ask you to go ahead and select your responses. We'll take just a few seconds to let folks respond. Probably another 20 seconds or so. Looks like people are actively filling in their reaction. Got about 70% of the folks have responded. I will close this. and share it. Is that what you were expecting to see, Dennis?
You know, I'm looking at that, and I think that's probably true. It's just structural problems, problems with the language. Usually SMEs can tell you when the items are difficult or easy. Sometimes answer key issues. So that's interesting to see. Thank you. Thank you all for responding to that.
I will close the poll and let you continue.
And we are going to turn the time over to Dan Allen now so he can talk about observations he's made on some data and items with this analysis.
Thanks, Dennis. Let's just jump right into the slides then, I guess. So I took the analysis from a single exam, and we got some subject matter expert feedback and combined that with also the answer key strength analysis, and just had a few example items and some observations. So I've disguised my items clearly to preserve the security of them, but I've maintained the structure of what was discovered, and so you could hopefully still learn something from it. So this first item, SME feedback suggested that this item was too text specific, and so what we'll have is a lot of students guessing and using test-taking strategies of one form or another. And so what we had was a large number of students selecting A and a large number of students selecting C. And you can see that the correct answer is denoted by the asterisk there. And another thing that students might have been doing is selecting C because it is the only negatively worded response of the available options. So because of this, we were getting an ambiguous key, and the revision step is to totally revise the item so that it is no longer too text specific, and also to conform to our style guide, we would take out the rival options A and C. Next slide, please. Here's another example of an ambiguous, an item that was flagged as having an ambiguous key. You can see on option A, which is also the correct response, our subject matter expert suggested that we should substitute the word real for the word anticipated, because for reasons that they understood, that the highest scoring students were being turned off to that response and instead selecting C. So after changing this to something that won't make A partially incorrect, which is what the wording was doing, we fixed it to be the clear correct response. And hopefully that'll fix. I don't have any data yet on, I should say I don't have enough data yet to say whether we fixed it or not, but hopefully that'll come out as not being ambiguously keyed in the next analysis. Next slide, please.
Hey, Dan, before you start talking to this slide, I see that some people have used the GoToWebinar dashboard to raise their hands virtually. Folks, if you're doing that to ask a question, I'd ask you to go a little further down in the dashboard and write out your question, please. Thank you. Sorry, Dan.
Not a problem. This next example was flagged as having a weak key, and it has 3 correct responses, all of which need to be selected by the student. We had, in this example, high-performing students correctly, and really not just high-performing students, but all students were picking C and D correctly. But the high-performing students were as likely to pick E as they were to pick A, and subject matter expert feedback suggested that E may be a reasonable answer to the question. So in the revision workshop, they had decided to make only one of the answers correct and substitute both E and two of the previous correct responses with answers that were clearly incorrect. Next slide, please. This is the last example item I have to share today. This was flagged as having a potential miskey. And this is an interesting story about this item. We had another issue with a negatively worded response for B, which doesn't conform to our style guide when one of the distractors sticks out like that and has negative wording where the others don't. And on top of that, we had about 10 administrations on this item, which isn't really enough to make a solid decision, but every single response had picked B, and that was enough to concern me about this item to take a look at it again. So I sent this item back to our editor, and I said, I understand this item just came out of a workshop with subject matter experts. It still seems to have some issues. Could you take a look at it? And he got back to me the next day. This was just last week, and he got back with his subject matter experts, and for whatever reason, the editing on this item hadn't made it all the way through, and so it had been republished with an incomplete fix. And so this item had, in fact, been miskeyed, and so the flag of potential miskey was correct in this case. That the correct response should have been B, and for a data entry error, it wasn't caught, but it was correctly flagged as having potentially been miskeyed, as actually being miskeyed. So that was helpful and helped us catch an actually miskeyed item. So that was good. So that's all I had. If there's any questions, I can take them at the end, I guess. So thanks, Dennis.
Well, thank you. Let's go to the next slide. So these are slides prepared by Barbara Foster of the American Board of Obstetrics and Gynecology. She will be proud I pronounced that properly. Let's go forward. Barbara is in Washington, as I said today. So this is data from their 2013 certifying exam. They have 180 scored items. There are also 5 sets of 40 field test items on the forms. There are 5 forms. Total exam length is 220 questions. Total number of items would be 180 plus 200, or 380. Let's go forward, please. And what the American Board of Gynecology and Obstetrics, ABOG, what the ABOG did is they looked at these potential miskeys, these flags that we gave them. 8 were identified among scored items. 22 were identified among the field test items. And it's not surprising that you would have more flags for field test items. Those are tryout items, they're new items, etc. So there were 30 total flags here. Let's go forward. And the SMEs reviewed all these data. And 4 of the 8 flagged scored items were found to have problems. So 4 of those had problems. They were ambiguous wording, new information was just published prior to the exam, changes in guidelines, etc. You can read that. So as a result of that, these items, they were scored, they had problems, they were deleted before the final scoring of the exam from scoring. And that's in order to get reliability up, right? Okay, let's go forward. There were 22 flagged field test items. Of those, 15 or 68% were found to have problems. And again, ambiguous wording, responses that were too closely related, changes in the actual, in the field, in the technical area. It actually caused some of these items to be wrong also. Let's go forward. So what are interesting here is Barbara has compared questions that were flagged with their standard methods at ABOG, and then these that she called the STAR method, which is this probability, this key strength analysis we call it. So there were 22 field test questions, 8 questions that were, and the 8 items flagged by both, and 27 flagged by the standard method. So you can see there's some overlap, but a lot of non-overlap also, which is helpful. It indicates that this is detecting something new and beyond, or in the additional to what they've already been detecting. Let's go forward. And so she summarized here where we had problems in these question sets again. So, this is, you can see those data. I'm not sure what Barbara would have said beyond what I've said, so I'll just move forward to the next slide, to the conclusion slide. So it indicates this method is detecting some things that were not being detected by the current methods. And it's not just keying errors, but it involves other important problem areas as well. I would call these structural errors, or structural flaws. So let's go forward. So it looks like we have a poll here.
Yep, and I'm not Johnny on the spot the way I should be. I was looking at questions. Let's launch this last question. Approximately how many field test items do you reject from further service due to poor statistics? This should be really interesting to see, and I'm sure it varies. We've got a number of folks voting, or answering the poll, I guess, responding. Take about 10 more seconds, get a majority here. All right, I'm going to close this up, Dennis, and share the results.
Well, that's consistent with what Dave Foster says. He says overbuild your pool. Maybe overbuild your pool by as much as 25%, because you're going to be rejecting a large number of questions. You often don't have time to go back and fix up the problems with the field test questions, so just to overbuild the pool. That's good. Thank you. Thank you for sharing.
Dennis, before we move on from Barbara's slides, there's a question posed. What are the current methods used by ABOG to flag items? What criteria based on the classical analyses? Do you know that, or is that something we should ask Barbara to weigh in on?
We'll need to ask Barbara later. She didn't share those with me, and I had the same question myself. Thank you.
Okay. Oops, I will hide the poll. And Dennis, we're at 53 after the hour. We do have a few questions we'll want to address.
Okay, I will do my best to wrap this up in 2 minutes. So classical item analysis in general helps ensure that we have unidimensionality, we have the desired item performance. One of the reasons we do this is to increase reliability, to improve internal consistency on the exams. This analysis we've talked about today, we call it key strength analysis, is an enhancement to classical item analysis. It uses the information from all items. We're comparing answer choices, and we perhaps have some reasons for poor performance on the items. And here's some areas of future research. I'm going to skip that, not talk about those. Instead, I wrote some discussion points. One user on LinkedIn remarked that the idea of detecting miskeyed items is not new or innovative. I agree, it's not. But this method we presented today is something we haven't really seen before. It extends classical item analysis in a principled way because it uses a model based on all of the items and all of the distractors. There was a question about point-biserial correlations and Z-star. It's important to realize doing a statistical test on Z-star is the same as doing a statistical test on the point-biserial because they're just related by a multiplicative constant. That's the square root of n-1. This key strength analysis contains implicitly within it a test on the point-biserial correlation with a threshold that's naturally suggested by Baezs model. Often you will see rules of thumb that say, well, you know, if the point-biserial is less than 0.2, 0.15, 0.25, you should discard the item. So what we have here is a threshold coming out of the data based on comparing all these items and the responses. If all the items are seen by the test takers, then the square root of n-1 factor is not an issue here at all. It's not important. So what that means for you is you can do the same analysis using all these corrected point-biserial coefficients yourself that come out of your standard statistical software. If the number of responses per item varies, like it would be with field test questions, more weight is given to the items with the highest administration values. And that feels right also. As you've seen, the key strength analysis will suggest when there's a potential key publication problem. If there's not a key publication problem, it will suggest when one of the alternative distractors is actually the correct answer. And I think it's important, as we've seen here, to have the SMEs review the items and share with them the distractor that was the most appealing or the strongest, so they can factor that into their review. You know, I think this approach has potential to analyze distractors that are less appealing also. I haven't looked at that. I think that's an interesting future area. And I think, as I said to begin with here, just in this section, that we want to find the poor performing items so we can improve test reliability. We haven't really here, Caveon, analyzed the impact of doing these procedures on reliability and following them, but I think it's promising. I think it can really help. And that is the end of this. Next slide, I think, is the question slide.
Okay. So, Dennis, before you turn things over to Dan, you were talking about validation. And a question was posed, would you not validate this method by comparing its ability to identify various kinds of poor items versus classical methods of identifying poor items?
Yeah, I haven't done that work. I mean, I've done this theory. We've been running this, looking at this. But there's a lot more future research to be done here. So part of our validation was the little study I shared with you. Also some empirical validation in terms of experience. It's anecdotal from Dan and Barbara. I haven't done a rigorous set of simulations. That's something for the future.
So there was a question about, earlier on, there was a question about has Dan or Barbara modified her key or given partial credit for previously non-keyed responses on the basis of these results? And I think the answer that we saw from Dan and Barbara is absolutely. The keys have been modified. The questions have been modified. One last question, Dennis. Could you expand on how this analysis could be used to help detect stolen content?
Oh, that's a really interesting question. We typically look at plots, scatter plots of p-value versus point-biserial. And what happens, you see interesting patterns arising when the content is stolen. When the content is stolen and a large number of the people are using the stolen content, you will see high p-values. In other words, items get easier, and high discriminations. They appear to be better items because the people who are using the content, they're all performing really well. And when you republish the exam with new questions, those questions all look like trash, even though they're good. So this analysis will augment that kind of analysis. And like I said before, you can use the extra key estimation also to help you with stolen content problems.
Excellent. There was a question I missed early on, Dennis. When you were showing formulas early, there was a question. It is the same point-biserial and biserial correlation. And I think what he's asking is, are the point-biserial and the biserial correlation the same? Did I ask that?
The same.
Okay.
The biserial correlation coefficient has a correction for assuming normality that you've dichotomized, and there's a multiplication factor that goes in there. I don't remember it off the top of my head. I don't usually use that. But it is used a lot, I know.
So we are up against the hour. There is another question, and we can stay on and answer that, but we really try to be sensitive to people's very busy schedules. So we thank everybody for attending. We will send you links to the slides and a recording of the session. The last question, Dennis, is, are there any published papers on this method available?
Not yet. We probably were premature, jumped the gun, but we need to work on publishing a paper. And we will do that. We're just really slow publishing here at Caveon because we have a lot of operational work we have to take care of also.
Yeah. And so if we go to the next slide, just I mentioned the Handbook of Test Security, co-edited by Jim Wallach and John Freemer. This is a wonderful, wonderful resource. If this is something you might want to obtain, the link below allows you to enjoy a pretty hefty discount. And with that, I think we've got one last slide. I'm not sure. It's a thank you. We thank Dan. We thank Barbara, Dennis, and Marcus. Terrific stuff as always. Attendees, thank you for investing an hour of your precious time to walk through this important new methodology. We hope this has been useful. We always appreciate your feedback and comments on how we can make these sessions better. So thanks in advance for any feedback you may lend. We'll see you next month when we tackle the important topic of online proctoring. Have a wonderful afternoon, folks. Thank you.